Tonight, we're going to sit with a single number. Not a dramatic number, not a number anyone shouts about. A quiet one, buried deep inside a scientific paper, collected by a satellite that spent 4 years doing nothing but staring at the faint afterglow of the early universe. And we're going to follow that number, slowly and carefully, all the way to its strangest conclusion, which is this. The universe almost certainly has no edge. No wall. No outer boundary you could ever reach. And if that's true, then somewhere out there, at a distance the math can write down exactly, there is another version of you. Same face. Same posture. Same breath you just took. Thinking, in this very moment, the thought you are thinking right now. That's not science fiction. That's not a fringe idea whispered at the edge of physics. That's what the cleanest reading of the data we already have quietly implies. And tucked behind it is something even stranger, the suggestion that the event we call the Big Bang, the beginning of everything, did not actually finish. That the engine which made you is, right now, still running. By the end of tonight, you'll understand why the truly unsettling thing about an infinite universe was never its size. The size is the easy part. The size has never been the frightening part. The frightening part is the reason behind the size, and we're going to take our time getting there. If you find this kind of slow, careful walk through the real physics worth your evening, it helps more than you'd think to subscribe. No pressure, no urgency. Just settle in, and if it earns it along the way, you can decide then. Now, let's begin. Let's start with where this story actually begins, which is not at the edge of the universe, but in the space right around your own body. Wherever you are right now, a chair, a bed, the floor, a train seat with the window going dark, I want you to stop thinking about the furniture for a moment, and think instead about the empty space. Not the chair beneath you. The space. The few centimeters of nothing between your hand and your face. The gap between your shoulder and the wall behind you. The hollow inside your own lungs as you breathe in. All of that emptiness, every cubic centimeter of it, was once part of something else entirely. It was packed into a region so small and so hot that the words small and hot barely apply. Around 13.8 billion years ago, the patch of reality that now holds you is not drifting and expanding the way it does today. Today the universe expands the way a cautious accountant grows a balance, politely, in measured increments, distances between galaxies stretching by a few kilometers per second for every few million light years between them. That's the modern, mature, slow-motion expansion. But back at the very beginning, in the first unimaginably small fraction of a second, the patch that became you was doing something else. It was doubling. Not slowly. It was doubling in volume on a timescale of roughly 10 to the minus 34 seconds, a tenth of a billionth of a trillionth of a trillionth of a second. Doubling and doubling again, and again, faster than light could ever hope to chase it down. Faster than anything the modern universe can do. And then, in your local patch, the patch destined to hold this chair and this body and this exact moment of attention, the doubling stopped. Whatever was driving that violent expansion, a field of energy filling all of space, rolled gently downhill and dumped everything it had into ordinary matter and ordinary light. The temperature spiked to something around 100 million degrees. Out of that heat, quarks froze into existence. Then protons and neutrons. Then the first atomic nuclei. Then, much later, whole atoms. Then stars. Then galaxies. Then planets. Then, on one particular planet, a chair, and a body sitting in it, and a mind placing its quiet attention on a piece of narration about the cosmos. That's you. That's the chain. That's the conventional story, and it is taught in essentially every introductory cosmology course on Earth. The Big Bang happened. We are the result. The end. But there is one sentence in that story that almost always gets skipped. And that single skipped sentence is the reason this whole night exists. Here it is. The inflation, that early, furious, light outrunning expansion, that produced your local patch did not stop everywhere. It only stopped here. It stopped inside the small, finite region we now call our observable universe. Just past the boundary of what we can see, just beyond a limit we'll spend a lot of tonight understanding, the math of the theory says inflation is still going. Not as a poetic flourish. Not as a metaphor a writer reached for. As a literal, physical prediction of the very equations that produced us. The engine that made us is still running. Hold on to that sentence. The first time you hear it, it sounds like a metaphor. By the end of tonight, I want it to sound like a flat description of fact. Because that's what it is. We talk about the universe as if it were a finished thing, an object with a size, a shape, a list of contents, the kind of thing you could in principle photograph from the outside the way you'd photograph a planet, if only you could find the right place to stand. But the universe may not be that kind of thing at all. The universe may not be a finished object. It may be an unfinished process. And the part of that process we happen to live inside might be one small, temporary, local off switch in a much larger machine, a machine that has been switched on for as long as we have existed, and which will keep running long after we are gone. So here's where we're headed, slowly, over the next couple of hours. We'll start with the measurement that hints the universe might genuinely be infinite, not just large, but truly without end. We'll walk through the inflation story properly, because most people carry only a blurry picture of what it actually claims. We'll arrive at a precise moment in the mid-1980s, when a physicist named Andrei Linde worked through the equations of his own theory and realized it was predicting something he did not want it to predict. We'll stand at the edge of something called the cosmic event horizon and feel, as carefully as we can, what it means to be sealed inside a sphere of cause and effect that is slowly shrinking around us. And by the time we close, you'll have the answer to the question the title quietly poses. Why is the universe infinite? And why is that infinity terrifying? The terror, I'll say one more time, was never the size. The terror is the reason for the size, the fact that the math keeps producing infinity no matter how hard physicists try to find a finite version that fits the data. And the reason it keeps producing infinity is that the same process which made us never finished. It started somewhere else, ran through the moment we call our Big Bang as one small local event, and kept on going. And by the structure of the theory itself, it has no off switch. Nothing tonight is invented. Everything sits inside the standard model of cosmology as it is currently taught. The strangeness isn't coming from speculation. The strangeness is coming from the data. So let's go slowly, and let's start with the word almost everyone gets wrong before they've even begun. Let's talk about what infinite actually means. When you hear the word infinite, notice what your mind does first. For most of us, the very first reflex is to reach for size. Infinite means big. Infinite means vast. Infinite means farther than any number you could name, in every direction, forever. You picture something like the ocean, except instead of stopping at a coastline, it just keeps going. Stars, then dark space, then more stars, more galaxies, on and on with no end anywhere. It's a natural picture. It's also, in almost every way that matters, the wrong one. Because in mathematics, infinite is not a size word at all. It's a structural word. It's a statement about a particular kind of arrangement, about how something is put together, not about how impressively large it is. And here's a fact that breaks the intuition cleanly in half. You can have an infinite collection that fits inside a tiny finite space. Picture a ruler, and on it, a segment exactly 1 inch long. The points along that 1 inch segment, the pure geometric points, with no width, form an infinite set. Not a large set. An infinite one, uncountably so, more points than you could ever list even in principle. And yet the segment itself is 1 inch long. You could pinch it between 2 fingers. Infinity lived inside that inch the whole time. So infinity in the precise sense isn't the answer to the question, how much? It's the answer to the question, what kind of thing is this? And when a cosmologist says space itself is infinite, they're not making a breathless statement about how big everything is. They're making a very specific claim about the shape of space on the largest scales. They're saying that if you picked a point, set off in a straight line, and walked forever, you would never reach an edge and you would never circle back to where you started. Space just keeps extending. Add up all the volume in every direction and the total is not a finite number. That, and only that, is what infinite means here. And the distinction matters more than it sounds, because the everyday meaning and the cosmological meaning quietly point in different directions, and most arguments about whether the universe is infinite are really two people talking past each other about two different things. Consider this. A universe can be enormous and still not be infinite. Think of the surface of the Earth. Stand anywhere on it and walk in a perfectly straight line. You will never hit a wall. You will never come to the edge of the world and fall off. There is no boundary anywhere. And yet the surface of the Earth is not infinite, it's about 510 million square kilometers, a definite, finite number. Walk far enough and you simply arrive back where you began, having gone all the way around. Finite, but with no edge. Mathematicians call that finite but unbounded. Now imagine that same trick performed not on a two-dimensional surface, but on three-dimensional space, a shape called a three-sphere. You could set off in any direction, travel forever without hitting any wall, and yet, if you went far enough, you'd eventually return to your starting point from the other side. That kind of universe is vast. It is not infinite. It just has no edge. And the reverse can be true too. A universe can be genuinely infinite and not feel cinematic at all. Imagine flat space stretching without limit in every direction, but sprinkled only thinly with galaxies, lonely and far apart. The volume is still infinite in the exact mathematical sense. But the lived experience of it might feel oddly empty rather than grand. So when people imagine the universe being infinite, they usually picture an infinite version of the night sky they already know, stars and galaxies tiled outward forever. That picture is roughly right in spirit and wrong in the details, because the real cosmological claim isn't about how many galaxies there are. It's about the geometry of space itself, and whether that geometry has a boundary, or wraps back on itself, or simply continues without end. There's a second mistake people make, and it's subtler than the first. We tend to assume that, is the universe infinite, is the kind of question you could answer by going to look. Build a big enough telescope, send out a fast enough probe, and eventually you'd find out whether the universe stops somewhere or keeps going. And this, in the strictest sense, is impossible. We are trapped inside a bubble of cause and effect, set by the speed of light and the age of the universe. The very farthest we can see in any direction is about 46 billion light-years, a boundary called the particle horizon, the distance light has had time to cross since the beginning, once you account for the fact that space itself has been stretching the whole way. Beyond that distance there is more universe. It's there. It's real. But no light from it has ever reached us, and, this is the part that catches people, no light from it ever will, because the expansion of space is carrying it away faster than any light it sends could close the gap. That isn't a temporary problem we'll engineer our way past. It's not a question of waiting for a better instrument. It's a permanent feature of our situation. The universe extends past the limit of what we can ever see, and the question of how far past, finitely far, or infinitely far, is simply not something we can settle by looking directly. So why do physicists talk about infinity at all, if we can't see far enough to check? Because the question can be approached sideways. We can't measure infinity. But we can measure the shape of the part we can see. We can measure how flat, or how curved, the local universe is. And then, using one carefully stated assumption, we can extend what we find locally to the whole. That assumption has a name. It's called the cosmological principle, and it says something almost humble, that no part of the universe is special. On the largest scales, the universe looks the same everywhere, the same density of matter, the same rate of expansion, the same physical laws operating in every direction. If that's true, and if the patch we can measure turns out to be flat, then the whole thing, by extension, must be flat too. And a flat universe, under the standard reading of the geometry, is spatially infinite. That assumption is doing an enormous amount of work, and it's worth being honest about it. The cosmological principle is an assumption, not a measurement. It might be wrong. It's consistent with everything we've observed so far, but it isn't proven, and there are a few corners of the data where it sits under mild strain. Keep that in your back pocket. We'll come back to those tensions later, because they matter. But for now, grant the assumption. Grant that the universe is uniform on the largest scales. Then the whole question of whether the universe is infinite collapses down into one measurable thing, the shape of the patch we can actually see. And when we measure that patch carefully, it comes back looking remarkably, almost suspiciously, flat. That's where we're going next. Because the universe, by the best measurement we have, is not best described as big. Big isn't even the right word. The universe is flat. And flat, under the standard assumption, means something very specific, something that should make you pause. In March of 2013, a satellite called Planck released its first major batch of results about the universe's basic parameters. 5 years later, in 2018, the team published the final set, in a long and now famous paper, the kind of paper that gets cited thousands of times. Among dozens of carefully measured numbers, there's a single line that quietly changes how a thoughtful person ought to picture the size of everything. It's the value of something called the spatial curvature parameter, written by physicists as omega k. And the number Planck pinned down for it was 0, give or take 0.5%. That's the whole story, sitting in one line. But to feel why it matters, you have to understand what that parameter is. In Einstein's general theory of relativity, space is allowed to curve, and it can do so in three basic ways. It can curve positively, like the surface of a sphere, bending back on itself. It can curve negatively, like the middle of a saddle, flaring outward. Or it can be flat, like an enormous tabletop. The curvature parameter is just the number that tells you which of those three you're living in. A positive value would mean a closed, spherical universe, finite in volume, the three-dimensional cousin of the surface of the Earth. A negative value would mean an open, saddle-shaped universe, infinite in extent. And a value of exactly 0 would mean a flat universe, which, under the standard reading of the geometry, is also infinite. Planck's answer was 0, to within 0.5%. The universe is flat, or so close to flat that any curvature, if it exists at all, is too gentle to matter for the patch we can see. Now, cosmology is a field that has been burned by overclaiming before, so honesty about the error bars matters here. The measurement is consistent with the universe being exactly flat. It's also consistent with a whisper of positive curvature, a closed universe, but a staggeringly enormous one. And it's consistent with a whisper of negative curvature, an open universe, even more infinite, if that phrase means anything. The data does not slam the door on a finite, closed universe. What it does is set a floor on how big such a universe would have to be. If the universe is closed, the measurement says, then the radius of that great sphere has to be at least about 250 times the radius of the observable universe. That works out to something like 11,500 billion light-years. It's a finite number. But it's a finite number so large that from inside our little patch, the universe is functionally indistinguishable from one that is exactly flat and exactly infinite. So when physicists discuss the Planck curvature measurement, they're really saying two things at once. They're saying the universe is, at the very minimum, vastly larger than the part we can see. And they're saying that under the simplest interpretation, exact flatness, the simplest possible shape, the universe is straightforwardly, endlessly infinite. I want you to feel how this number was actually obtained, because it's easy to let "a satellite measured the universe" wash over you as a slogan. Picture it concretely. Engineers built a spacecraft and sent it not into orbit around the Earth, but out to a special, gravitationally calm spot about 1.5 million kilometers away, on the far side of Earth from the Sun. They pointed its exquisitely sensitive heat detectors at the sky and held them there for 4 years. What those detectors were drinking in was the oldest light in existence, the faint, cold glow left over from when the universe first became transparent, a relic radiation now chilled to just a few degrees above absolute zero. They measured the temperature of that glow across the entire sky to an accuracy of about 1 part in 100,000. Then they studied the pattern of tiny warm and cool ripples printed across it, measured the characteristic size of those ripples, and from that size, from the angle those ripples subtend in the sky, they read off the geometry of the universe. It works the same way it would on Earth. Draw a triangle on a curved surface and the angles won't quite add up to 180 degrees, the bigger the triangle, the more they overshoot. Draw the cosmic equivalent, measure features of a known size at a known distance, and ask what the angles come to. The answer came back at 180 degrees, to within the precision of the instrument. The universe is not curving back on itself. The universe is not flared like a saddle. On the largest scales we can reach, the universe is flat. And here is the implication the Planck team was very careful not to shout, but which now sits quietly in the conclusion of every cosmology textbook updated since these results came in. If the universe is flat, and if the cosmological principle holds, if the universe really is the same everywhere on large scales, then the universe is spatially infinite. It extends without bound. It contains an infinite number of galaxies. An infinite number of stars. And, we'll get to this slowly and carefully, because it deserves it, by a simple counting argument, an infinite number of copies of every possible arrangement of matter that the laws of physics allow inside a region the size of ours. This is not a fringe reading. This is the standard textbook conclusion drawn from a flat universe under the cosmological principle. It's the operating assumption working cosmologists carry into their day jobs. And notice what just happened, because it's quietly remarkable. We went from the question, is the universe infinite, to the answer, yes, probably, by the cleanest reading of the data, and we did it without ever invoking anything exotic. No multiverse. No speculation. Just one measurement. Just the curvature of space coming back flat, plus the assumption that the universe is uniform on large scales. That's the first half of the story. The second half is the question this whole night is really about. Why is it flat? Why does the measurement come out at exactly zero curvature, rather than the value you'd expect from a closed, finite universe? What is the engine driving the geometry of space toward such perfect flatness? Because that engine has a name. And once we understand how it works, we're going to find a result buried inside it, a result the people who invented the theory did not want to find. We're going to find the reason the universe isn't just probably infinite, but predicted to be infinite. The reason behind the reason. That engine is called inflation. And to understand why it might make the universe infinite, you first have to understand the problem it was invented to solve. So let me take you back to the very end of 1979, into the first weeks of 1980, to a young physicist working late at a particle accelerator in California, chasing a technical question that, on the surface, had nothing whatsoever to do with the size of the cosmos. His name was Alan Guth, and in those final weeks of 1979 he was working at the Stanford Linear Accelerator Center, deep inside a problem that belonged, as far as he was concerned, to particle physics, not cosmology. He was thinking about grand unified theories, the ambitious family of ideas that tries to fuse three of nature's forces, electromagnetism and the weak and strong nuclear forces, into a single description that holds true at enormous energies. And within that, he was chewing on a narrow technical question: what happens to a certain kind of quantum field if it gets stuck, as the universe cools, in a state it can't easily escape? He sat down and worked out the calculation. And in his notebook, when the answer came, he wrote two words next to it that have since become a little famous among physicists. He called it a spectacular realization. Here's what he'd found. Suppose there's a field, some quantum field with the right shape to its energy, and suppose that very early on, while everything was unimaginably hot, this field got trapped in what's called a false vacuum. A high-energy state it couldn't immediately roll out of. A field stuck like that, Guth realized, would behave gravitationally in a very particular way. It would act like a constant energy filling all of space, the same density everywhere, never thinning out. And Einstein's equations have a stark thing to say about a region of space filled with a constant energy density like that. Such a region doesn't just expand. It expands exponentially. It doubles, and doubles, and doubles, faster and faster. And this wasn't a gentle doubling. This wasn't the universe growing once every billion years. The natural timescale that fell out of the simplest versions was a doubling roughly every 10 to the minus 34 seconds. Let that sink in for a second, even though no human intuition can really hold it. A region of space the size of a single proton, undergoing this kind of expansion, would balloon up to the size of the entire observable universe in less than 10 to the minus 32 seconds. Not as a figure of speech. Literally. The math says so. And Guth saw that if a phase like this had genuinely occurred in the first sliver of the universe's existence, it would solve, in one stroke, 3 deep problems that the ordinary hot Big Bang model simply could not explain. The first was the horizon problem. When we look at that ancient relic glow, the cosmic microwave background, we find it has very nearly the same temperature in every direction, equal to about 1 part in 100,000. Point your detector at one edge of the sky, then swing it a full 180 degrees to the opposite edge, and the 2 patches you measure are at the same temperature to astonishing precision. The trouble is, in the standard Big Bang picture, those 2 patches have never been in contact. Light from one of them has never had time, in the whole history of the universe, to reach the other. There is no signal, no influence, nothing that could have traveled between them to even them out. Yet they match. It's as though you walked into 2 houses on opposite sides of a city you'd never visited, with no shared heating, no shared anything, and found the thermostat in each set to exactly the same temperature, down to the last decimal. You'd suspect they were connected somehow, once, before they were separated. And that is precisely what inflation says. If everything we now see was once packed into a region small enough to reach a common temperature, and was then stretched, by a factor of at least 10 to the 26th, out to cosmic size, then the uniformity we observe was simply inherited. The smoothness was settled long ago, when all of it was crammed into a space smaller than an atom and could comfortably reach equilibrium. Inflation just took that smooth little patch and blew it up. The second was the flatness problem. We just spent a long while on the fact that the universe is flat today, to within 0.5%. But there's a hidden difficulty in that. Any deviation from perfect flatness in the early universe doesn't stay put, it grows, and grows quickly, as time goes on. For the universe to be as flat as it is now, it must have been almost incomprehensibly flat at the very beginning. Run the numbers back to the earliest moment physics can describe, and the curvature back then had to be 0 to within 1 part in 10 to the 60th. That's a 1 followed by 60 zeros in the denominator. That is not a delicate balance, that is a number so close to 0 it screams for an explanation. In physics, when you find a coincidence that extreme, you don't shrug and call it luck. You take it as a sign that something in your model is missing. And inflation supplies the missing piece, in the same motion that solves the horizon problem. Stretch any surface enough and it flattens. Blow up a balloon and the patch of rubber under your thumb goes from sharply curved to nearly flat. Inflate the universe by that factor of 10 to the 26th, and whatever curvature it started with gets ironed out far below anything we could ever detect. Around 50 or 60 doublings, physicists call them E-folds, is enough to do it. And the third was the monopole problem. Those same grand unified theories Guth had been working on make a confident prediction: the early universe should have produced a flood of magnetic monopoles, isolated magnetic charges, particles carrying a north or south pole all on their own. And not a few of them. The predicted abundance is so high that monopoles should be one of the dominant forms of matter in the universe today. They should be everywhere. We should be tripping over them. And yet we have looked, in cosmic rays, in ancient mineral samples pulled from deep underground, in particle accelerators, and across more than 50 years of searching, the confirmed count stands at exactly 0. The ordinary Big Bang has no answer for where they all went. Inflation answers it by sheer dilution. If the universe inflated by that same staggering factor after the monopoles were made, their density would have dropped by a factor of around 10 to the 78th, diluted so thoroughly that the expected number anywhere inside our entire observable universe falls to about 1. Effectively none. The monopoles aren't gone. They're just spread so impossibly thin that the odds of even a single one sitting inside the part of the universe we can see are negligible. 3 stubborn problems, dissolved by one idea. The exponential stretching of a tiny patch of the very early universe, driven by the energy of a field trapped in a false vacuum. Guth gave it a name, inflation, and published his original paper in 1981, in the journal Physical Review D. The title was modest and exact, a proposal that inflation might solve the horizon and flatness problems. It became one of the most influential papers in 20th century cosmology. But Guth's first version had a flaw, and it's worth understanding, because the fix is where the real strangeness eventually enters. In his original picture, inflation ended through something like the boiling of water. Inside the false vacuum, little bubbles of the true, lower energy state would form, and those bubbles would grow, and eventually they'd all merge together and fill space with the ordinary post-inflation universe. The problem was the merging. In his model, the bubbles couldn't keep up. The inflation they were trying to end kept hurling them apart faster than they could meet and coalesce. You'd end up with a universe full of isolated bubbles drifting in an ever-inflating background, something like Swiss cheese, all holes and no smooth hole. And that does not look anything like the smooth, even universe we actually live in. The repair arrived in 1982, from a Soviet physicist named Andrei Linde, in a paper proposing what he called new inflation. Linde's insight was to change how the field behaves. Instead of being trapped and then escaping through a sudden, jagged phase transition, the boiling bubble picture, his field rolled slowly. Imagine a ball resting near the top of a very gently sloped hill, easing its way down. While the field is up near the top, the energy stays high and the exponential expansion runs exactly as before. But because the descent is smooth and gradual, inflation ends gently and all at once across the whole region, instead of fracturing into bubbles. No Swiss cheese. The universe comes out smooth. This slow-roll version became the standard picture almost immediately, and it has survived 4 decades of relentless testing. The flatness, the smoothness of the background glow, the absence of monopoles, and the precise statistical pattern of the tiny ripples imprinted on that ancient light, all of it was checked, again and again, by a succession of increasingly precise instruments, COBE in 1992, WMAP in 2003, and Planck in 2013 and 2018. One of inflation's sharpest predictions was a specific number describing the tilt of that ripple pattern. It should come out slightly less than 1. The measured value landed at about 0.965. Almost exactly where the theory said it would be. So I want to be clear about something, because the word theory gets thrown around loosely. Inflation is not a wild guess. It is the leading framework for the first fraction of a second of existence, supported by several independent lines of evidence, making quantitative predictions that have passed precision test after precision test, across multiple satellites and multiple decades. That's the inflation story as it's usually told. A young physicist had a spectacular realization. It solved 3 nagging problems. The math worked. The data agreed. The end. Except it isn't the end. Because there's one more piece of this story that doesn't make it into the introductory courses, and that piece is the entire reason we're here tonight. It's a piece Andrei Linde stumbled into 4 years after his new inflation paper, while he was working through the consequences of a slightly different version of the theory. It's the piece he did not want to find. It's the moment the math began producing infinity even though no one had asked it to. Let me take you into that. In 1986, Linde published a paper with a long, almost confessional title, about an eternally existing, self-reproducing inflationary universe. It's one of the most consequential cosmology papers of the late 20th century, and the result inside it is the thing this entire night has been quietly building toward. The paper concerns a particular flavor of inflation that Linde himself had introduced a few years earlier, called chaotic inflation. In this version, the field doesn't start out trapped in some special false vacuum that has to be carefully arranged. Instead, it simply begins at some high value, set by random quantum fluctuations back at the earliest, most extreme energies, and then rolls down from wherever it happens to start. Different regions of the early universe begin with different values of the field, so different regions inflate by different amounts before they finish. In a way, it's a more natural picture than the trapped one, because it doesn't require the universe to have been prepared in any delicate state. It just requires the field to fluctuate, which is exactly what quantum fields do, and the regions that happen to start higher inflate more. Linde was working through the behavior of this picture, and he ran into something strange. He was thinking about how the field changes during inflation. The classical, smooth equation of motion says the field rolls steadily down its slope, and where it reaches the bottom, inflation ends and the energy converts into matter and light. Straightforward. But there's a second ingredient he couldn't ignore, because it's built into the deepest level of how reality works. The field, like every quantum field, fluctuates. It jitters. These fluctuations are small, but they are not zero, and in a region that is itself expanding exponentially, those jitters get stretched out along with everything else. So Linde asked a simple question. What happens in the regions where the quantum fluctuation happens to push the field upward, back up the hill, against the classical roll that's trying to bring it down? And here is the heart of it. In those regions, the field value gets larger, not smaller. So inflation doesn't end there, it keeps going. And because the local rate of expansion is set by the field, higher field, more energy, more vigorous inflation, those upward fluctuating regions don't just keep inflating, they inflate faster than their neighbors. Their volume grows more quickly. Now picture the whole population of regions across the inflating universe at any given instant. Some have rolled down and are finishing, converting into ordinary universes like ours. But others have fluctuated upward and are inflating harder, swelling in volume faster than the finished regions are being made. When Linde worked out the balance, the math said something he had not been looking for. In the simplest versions of chaotic inflation, the upward fluctuating, still inflating regions reproduce themselves faster than they are used up by the regions rolling down to completion. At every moment, somewhere, inflation is ending, but the inflating part is always winning the race, always making more of itself than it loses. The finished regions, the calm pockets that become universes, are just isolated islands inside an inflating background that never stops, that simply goes on inflating forever. This is eternal inflation. And the name is exact. The inflation does not end. It continues into the indefinite future, with new finished bubbles forming inside it at a steady rate, while the inflating volume between them grows without limit. Each bubble, from the inside, looks like a complete and self-contained universe, a finite region with its own beginning, its own expansion, its own history unfolding. But from the outside, from the vantage of the inflating background, that bubble is just one small local event in a much larger process that was running before it formed and keeps running long after. There's a story told by people who were around during that period of cosmology, and it's the human core of all this. Linde, by these accounts, did not want this result. He didn't present it as a triumphant feature of his theory. He published it because the math required him to. Think about his position. He had spent years on inflation. He'd built multiple versions, refined the dynamics, fit the predictions to the data. He was deeply invested in inflation as the theory that explains the universe we actually see. And then his own theory, when he ran it carefully and honestly, started predicting something far beyond explaining the universe we see. It predicted that the universe we see is one bubble among an unbounded number of others, scattered through an inflating background that has been running for as long as anything has run and will keep running with no end. He published anyway. Because that's the discipline. A physicist working through equations is allowed to dislike the answer. He's allowed to look for an error, to argue the result is an artifact of some simplification, to hunt for a way around it. What he is not allowed to do is make the answer go away by wishing it would. The math kept producing it. So Linde wrote the paper. That was 1986. And around the same time, working independently, a physicist named Alexander Vilenkin arrived at much the same conclusion. Guth himself came to it later. By the early 1990s, eternal inflation was understood across the inflation community not as some enthusiast's embellishment but as the generic outcome of the theory, the thing that simply falls out when you let the equations run. Not every conceivable version of inflation produces it, you can build carefully tuned models that avoid it. But the simplest, most natural versions, the ones that match the data most cleanly, all produce it. Now, there's a subtlety here worth pausing on, because it has a strange weight to it. Eternal inflation is future eternal. It never stops going forward. But it is not past eternal. It had a beginning. In 2003, three physicists, Bohr, Guth, and Vilenkin, proved this in a short, sharp paper with a blunt title, that inflationary spacetimes are incomplete in the past. The proof showed that any universe in which space has been expanding on average over its history must have a past boundary, a moment before which it simply did not exist. So eternal inflation has a start. What it lacks is an end. The past is finite. The future is unbounded. And that asymmetry has an unsettling consequence for our sense of where we sit in all this. We tend to imagine ourselves as cosmologically late, long after the Big Bang, somewhere in the comfortable middle of cosmic history. But if eternal inflation is right, that's exactly backwards. Every moment that passes, more bubbles form, more inflating volume is added, and the total grows without limit into the future. By the logic of it, the overwhelming majority of everything that will ever exist lies ahead, not behind. We are not in the middle. We are at the very beginning. There is almost nothing behind us, and an unbounded process stretching out in front. Try, for a moment, to stand where Linde was standing when he understood this. Picture the equations on the page, the field equations of inflation, with their exponential solutions and their little quantum fluctuation terms. Picture someone working through them, expecting them to behave the way they've behaved in every paper he's written for 3 years, describing a patch that inflates, then settles smoothly into a hot Big Bang, after which ordinary cosmology takes over and the story ends. And then picture the moment the fluctuation term refuses to average out the way it's supposed to. The moment the volumes don't balance. The moment the upward jitters sustain inflation faster than the steady roll can consume it, and the math says, plainly, this does not stop. There's no drama in the equations themselves. Just symbols on a page, doing what symbols do. But the person reading them doesn't get to choose what they say. He can disagree. He can search for a way out. He cannot make it untrue by preferring it to be. The math kept producing it. He wrote the paper. And 40 years later, eternal inflation is still the default prediction of the standard model of cosmology, still the thing that falls out of the equations when you let them run. Physicists have spent those 4 decades trying to build a version of inflation without the eternal part, and they've succeeded. On paper, there are specific models that produce a single finite inflating patch and then genuinely stop. But those models are delicately tuned, and there's no evidence nature chose them. The generic inflation, the inflation that matches what we measure, is eternal. To escape the prediction, you have to make the theory more complicated, and the more complicated theory doesn't fit the data any better. So the prediction stands. And this is the engine. Hold that word, because we'll keep returning to it. Eternal inflation is the reason the universe is infinite, and notice it's a different reason than the flat geometry we measured earlier. The flatness is an observation. The cosmological principle is an assumption. But the engine is the active mechanism, the thing physically producing more universe than will ever fit inside our horizon, the inflation that simply has not ended. So the natural next question is, where? Where is it still happening, if it isn't happening here? And why, if it's real, can we never see it? To answer that, we have to walk up to one of the strangest and least discussed objects in all of cosmology, a boundary that is not a wall, not an edge, not a place. A boundary defined entirely by cause and effect. It's called the cosmic event horizon, and once you understand what it is, where it sits, and how it behaves as the universe's expansion accelerates, you'll understand why the engine, even though it's still running, is something we are sealed off from forever. Let me be careful about what the cosmic event horizon is, because it's easy to confuse it with something it isn't. It is not the edge of the universe. There is no edge. It is not a surface you could fly up to and touch. It's a boundary defined by a single question: can a signal sent from where you are, right now, ever reach a given point out in the distant universe? Under our best current model of the cosmos, refined by the most recent surveys through 2025, the present distance to that boundary is roughly 16.5 billion light-years. That's the distance, measured right now in this moment, beyond which anything you send today, a radio pulse, a flash of light, a message, will never, ever arrive, no matter how long you wait. The expansion of space, accelerated by the mysterious dark energy that dominates the modern universe, is carrying everything past that line away from you faster than light can chase it down. Once a galaxy crosses that boundary, any light it emits afterward will simply never reach you. And this is a different boundary from the one we met earlier. Remember the particle horizon, the farthest we can see, about 46 billion light-years out, set by how far light has had time to travel toward us since the beginning. The particle horizon is about the past, it's the limit of how far back, and how far away, we can see. The event horizon is about the future, it's the limit of how far out a signal we send today can ever reach, and the limit on what can still send signals to us. The event horizon is the closer of the two. And here's a way to feel the difference. Light from galaxies near the particle horizon is reaching us right now, but it left those galaxies in the deep past, when they were much closer than they are today, and we're only now receiving it. The event horizon, by contrast, tells us which of those galaxies can keep sending us new light into the future, and which have already been carried too far for anything new from them to ever arrive. Most introductory treatments dwell on the particle horizon, because it's the edge of what we can see, and that's easy to picture. The event horizon gets far less attention, because it's a boundary about what we will never see, and that's a much harder thing to develop a gut feeling for. But for our purposes tonight, the event horizon is the more important of the two. Because everything beyond it is cut off from us, causally, forever. We can never send a signal to anything past it. We can never receive a signal from anything that happens past it. It is a wall not on what exists, but on what we can ever know. And here's the consequence that ties it all together. If eternal inflation is real, if the still inflating background is out there and new bubble universes are still forming inside it, then all of those bubbles must lie beyond our event horizon. They have to. Because if any of them were inside it, we'd be able to detect them. We'd see their fingerprints in the local glow of the cosmic microwave background, in the way matter is distributed around us, in the large-scale structure of our own sky. And we don't. For decades of looking, and we don't. Which tells us that whatever other bubbles exist are sitting on the far side of a boundary we will never cross. The engine is still running. But it's running on the other side of a wall we can never reach. There's a piece of this that doesn't get said often enough, and it changes the feeling of the whole picture. The event horizon is not fixed. Under accelerating expansion, it doesn't sit politely at 16.5 billion light-years and stay there. It moves inward. It shrinks. Slowly, relentlessly, the boundary of what we can ever reach is closing in around us. Galaxies that are inside our event horizon right now will, given enough time, drift outward across it. And once they cross, they're gone, not destroyed, not vanished, just permanently removed from the volume of space we can ever interact with. The light they emitted before the crossing will keep arriving at our telescopes for billions of years afterward, growing fainter and more stretched, more deeply reddened, sliding toward an infinite redshift. But nothing they emit after the crossing will ever reach us again. And this isn't a distant abstraction. Right now, somewhere on the sky, a galaxy is crossing our event horizon. It sits at a distance of about 16.5 billion light-years from this chair, from your body, from wherever you happen to be sitting. Through a telescope it looks like any other faint, ancient, reddened smudge, light that's billions of years old. But inside that galaxy there are stars, and around some of them, very possibly, planets. And on some of those planets, by the symmetric logic of cosmology, there may be observers no different in any meaningful way from you, beings looking up at their own sky, wondering their own version of these same questions. And in this exact moment, the moment of crossing, any signal that galaxy might be sending toward us, any beacon, any flash, any deliberate hello aimed at the dark, is being severed from us forever. The galaxy is still there. It is not winking out. It is simply being carried, permanently, beyond the edge of everything we can ever touch. And there are uncountable galaxies in exactly this situation, with more joining them every minute. The horizon keeps tightening. If you run the clock forward, the long future of our patch is a story of deepening isolation. By around 100 billion years from now, the only galaxy left inside our event horizon will be our own, the Milky Way and Andromeda, by then long since merged into a single great elliptical, plus a scattering of small satellite galaxies that came along for the ride. Everything else will have crossed outward. The night sky, beyond our merged home galaxy, will be empty of any other galactic light. Observers living then, if there are any, will look out and see a single island of stars surrounded by perfect darkness, with no way of knowing, from observation alone, that the universe was ever full of galaxies at all. That's the long fate of our bubble. Slow causal isolation. The steady removal of the rest of the universe from our reach. And out there, beyond the shrinking wall, the engine of inflation keeps running, new bubbles keep forming, and the math keeps producing infinity, none of which we will ever see. We'll be locked inside our local patch, watching it grow lonelier, while the rest of the inflating cosmos unfolds without us. And yet, there is one place in the entire observational record where the wall may have leaked. One anomaly in that ancient relic glow that could, in principle, be the faint fingerprint of another bubble brushing against ours, long ago, in the inflating dark. It's by some readings the closest thing we have ever found to direct evidence that the engine is real. It's a cold spot, and it lies in the constellation Eridanus. Let me show you what it is, and why it's both tantalizing and, in the end, unproven. That relic glow, the cosmic microwave background, has an average temperature of about 2.725 degrees above absolute zero, cold, even, almost boringly uniform, with fluctuations of only about 1 part in 100,000. In most respects it is the most monotonous object in all of existence, the same temperature in every direction to a precision that almost defies belief. But there's one feature that doesn't quite fit. In the direction of Eridanus, at a particular set of coordinates on the sky, there's a region that runs cold, about 70 millionths of a degree colder than the average, dipping to as much as 150 millionths of a degree below the mean at its deepest. And it's large, roughly 10 degrees across the sky, which at the distance of that ancient light corresponds to a physical scale of something like 300 million light-years. By the standard statistical analysis, it's anomalous. The odds of a cold region this extreme showing up purely by chance, in a universe behaving exactly the way standard inflation predicts, are on the order of 1 in 1,000. The cold spot was first identified in 2004, and in the 20 years since, it has been one of the most poked at, scrutinized features of the whole microwave sky. The basic finding has held up: there is a genuine cold region in Eridanus, it is statistically unusual, and it does not slot comfortably into the simplest version of the standard picture. There are two main ways to read it. The first is conventional, and almost certainly accounts for most of what we see. The idea is that the cold spot is caused mainly by a vast emptiness in the foreground, a region of space, relatively nearby in cosmic terms, where the density of galaxies and dark matter runs well below the cosmic average. This emptiness has a name, the Eridanus supervoid, and it was identified by a galaxy survey in 2015. The mechanism by which a void chills the light passing through it is subtle but well understood. As ancient photons cross an enormous underdense region whose gravity is being stretched thin by the accelerating expansion, they lose a little energy on the way out, emerging slightly cooler than they went in. So the cold spot, in this reading, is largely a foreground effect, not a scar from the beginning, but a shadow cast by a hole in the nearer universe. The supervoid is real. The cooling effect is real. The only open question is whether the void explains all of the cold spot, or only most of it. And the honest answer, after the most careful analyses, is, most, but not necessarily all. There seems to be a little residual structure the void doesn't fully account for. It's statistically small. But it's there. And that small residual is what keeps the second interpretation alive. The second reading is the one this whole night has been circling. Beginning in 2006, a physicist named Laura Mersini-Houghton predicted, in a series of papers, that if our bubble universe had ever collided with another bubble forming nearby in the inflating background, the collision would leave a very particular mark on the cosmic microwave background, a roughly circular cold region, with a characteristic disc-shaped profile, at a particular angular size, with particular signatures in the polarization of the light. And here is what makes it interesting. That prediction was made before the cold spot had been thoroughly characterized. When the data came in, the qualitative match was striking. Not perfect, there are features of the observation that don't sit cleanly with the bubble collision idea, but close enough that it remains one of the most cited speculative readings of the cold spot in the modern literature. So let me be scrupulously honest about where this leaves us, because this is exactly what science looks like at the ragged edge of what can be tested. The cold spot is not proof of eternal inflation. It is not proof of a bubble collision. The mundane explanation, a huge void in the foreground, accounts for most of the signal, and the leftover is small. But the cold spot is, even so, the closest thing in the entire empirical record to a possible fingerprint of the engine. It's the one place where the wall might have leaked, just a little, just for a moment, billions of years ago. And the other searches have come up empty. In 2011, a team conducted the first systematic hunt for these disc-shaped collision signatures across the WMAP data, using a careful statistical procedure to look for exactly the patterns eternal inflation predicts. They found none that rose to significance. Later analyses with the Planck data, continuing through 2024, returned the same null result. The prediction of bubble collisions has never been positively confirmed. This is the empirical situation, laid bare. We have very strong theoretical reasons to think the engine is still running. We have one possible, contested, ambiguous fingerprint, the cold spot. We have systematic searches that have not found the cleaner signatures. And we have a permanent observational wall, the event horizon, that forbids any direct test of the prediction. The math is clean. The internal logic is sound. The fingerprints, where they exist at all, are ambiguous. And the honest conclusion is that we may never know for certain whether eternal inflation is correct. We may simply have to live with it as a permanent feature of our best theory, never confirmed, never refuted, sitting forever at the boundary of the testable. And some physicists are profoundly uncomfortable with that. They argue that a prediction which cannot, even in principle, be tested is not really a scientific prediction at all. This is not a small objection, and it deserves real engagement, because it brings us to one of the most public, most heated disputes in all of modern cosmology, a fight not about a measurement, but about what counts as science in the first place. In early 2017, a prominent science magazine published an article whose title borrowed the sound of a bursting bubble. It was written by 3 serious physicists, and that detail matters, because this was not an attack from outside the field by people who didn't understand it. One of the authors had been among the original developers of new inflation back in the early 1980s, he'd helped build the very theory he was now criticizing. Another was the chair of a major university's astronomy department and one of the most cited cosmologists of his generation. These were insiders, dismantling the paradigm carefully, from within. Their argument came in 2 parts. First, they claimed inflation had become so flexible that it could accommodate essentially any observational result, that with such a huge space of possible models, parameterized by all the different shapes the inflatant's energy could take, almost any measurement could be matched to some version of inflation. And a theory that can fit anything, they argued, ultimately predicts nothing. Second, and this is the part that bears directly on tonight, they argued that the eternal inflation extension made things not merely untestable but absurdly so. If eternal inflation generates an infinite ensemble of bubbles in which every possible outcome happens infinitely many times, then the theory predicts that everything happens somewhere. And a theory under which everything happens predicts nothing in particular. They gave this a memorable, slightly mocking name. They suggested the multiverse was less a triumph than a mess. That's the sharpest form of the falsifiability critique. It isn't just, we can't test it directly, which is the obvious complaint. It's, the theory predicts every possible outcome, so even indirect tests are meaningless, because whatever we observe is consistent with the theory having predicted it somewhere. The inflation community took the critique seriously enough to mount a formal, public answer. The very next month, a rebuttal letter appeared in the same magazine, signed by 33 physicists. And the names on that letter are worth dwelling on, because they tell you this is not a fringe quarrel. The signatories included the founders of inflation themselves, alongside some of the most celebrated names in 20th century physics, people whose work underpins much of how we understand the cosmos and the quantum world. Their argument ran like this. Inflation, in its standard slow-roll forms, makes specific predictions that have been tested and confirmed: the flatness, the smoothness, the tilt of the ripple spectrum, the detailed shape of the patterns in the ancient light. The fact that the theory has adjustable parameters does not make it untestable. Every theory in physics has free parameters. The standard model of particle physics, the most precisely tested framework we have, carries 19 of them, and no one says it predicts nothing. And as for eternal inflation, they conceded the obvious, that we cannot directly go looking for other bubble universes. But, they argued, eternal inflation is not a separate theory you could choose to bolt on or leave off. It's a consequence of inflation. If inflation is right, and inflation in its testable form has been confirmed to high precision, then eternal inflation follows from the dynamics. It's the price of the theory, not an optional extra. It's simply what the theory says when you let it run. That exchange remains one of the most public ruptures in modern cosmology, and it never resolved. The two sides did not reconcile. As of now, the dispute has gone mostly quiet in the technical literature, not because anyone won, but because both camps simply continued their work as though the other side hadn't spoken. And there are real, thoughtful holdouts. There are physicists who say that if your theory deduces something untestable, that's a reason to doubt the theory, not a reason to accept the untestable thing. There are physicists who reject inflation altogether, so the question of eternal inflation never even arises for them. There are physicists who insist the multiverse simply isn't science, no matter what chain of reasoning produces it, because it cannot be put to empirical test. These are serious positions held by serious people. But the majority view among working cosmologists lands closer to the rebuttal than to the critique. The mainstream position is that eternal inflation is a genuine prediction, made by a genuine theory, supported by genuine data, a prediction we may never be able to test directly, but which we should take seriously as a description of what the universe is doing beyond our horizon. And notice how unusual that is. We are used to theories that make predictions we then go and check. Inflation makes plenty of those, and the checks come back positive. But the eternal extension makes a prediction we cannot test from inside our bubble, and the community accepts it anyway, because it falls out of a theory that has otherwise earned deep trust. There's a name for this kind of reasoning in the philosophy of science: inference to the best explanation. We don't have direct evidence for the eternal part. But the theory that produces it is, in every aspect we can check, the best explanation we have for what we observe. So we extend the trust we've earned in its tested predictions to its untested ones, on the grounds that one theory produces both. We treat eternal inflation as real because the theory that says it's real has earned the benefit of the doubt. Whether that's good methodology or bad is a genuine philosophical question, and I won't pretend to settle it for you. But it is, in practice, the methodology the field has adopted. And the consequence is striking. When cosmologists talk shop about the universe, many of them talk about it as though eternal inflation simply were a fact. They speak of the bubble ensemble as real. They speak of us as one bubble among countless others in an inflating cosmos that is still, right now, doing its work. That is the strangeness this whole night is trying to make visible to you. Eternal inflation is not science fiction. It is not idle speculation. It is the default prediction of the very theory we use to explain why that ancient relic glow looks the way it does. It comes bundled with the package. And if you accept the package, which has been confirmed by every precision measurement we've managed to make, you accept the prediction. The math kept producing it. The community accepted it. And what it predicts is that we are inside a process still running, with no off switch, just past a wall we can never cross. So now let me take that picture and turn it inward, toward you. Because there's a consequence of all this that requires no exotic add-on at all. No eternal inflation. No bubbles. Just a flat, infinite universe with the same physics everywhere, the cleanest reading of the data we already have. And the consequence is one of the strangest results in all of modern cosmology. It was made explicit by the physicist Max Tegmark, first in a magazine article in 2003 and later, at length, in his 2014 book. The result has come to be called the Level 1 multiverse, and the reasoning behind it is almost embarrassingly simple. Suppose space is flat and infinite, we've established that's the simplest reading of the curvature measurement. Suppose further that physics works the same way everywhere, which is just the cosmological principle restated. Now think about a region the size of the patch we can causally interact with, a sphere about 16.5 billion light-years in radius. An infinite universe contains an infinite number of such regions, each one geometrically like ours, each one walled off from the others by its own horizon. And here is the crucial point. Each region contains only a finite amount of matter. The number of particles inside one is, depending on how you count, something like 10 to the 80th. And the number of distinct ways you can arrange those particles, given that, at the smallest scale, position and momentum come in discrete steps rather than a smooth continuum, is finite. It is unimaginably enormous, a number you'd have to write as a tower of exponentials. But it is finite. And now the logic clicks shut like a lock. If space is infinite, and physics is uniform, and the number of possible arrangements inside any one region is finite, then the arrangements must repeat. There are not enough distinct configurations to fill an infinite universe without reusing them. It's the pigeonhole principle, the same humble bit of counting that says if you have more pigeons than holes, at least one hole holds 2 pigeons. Stretch that to infinity, and every arrangement that exists in our region must exist, identically, in some other region. And not just once, in infinitely many others. Tegmark even estimated the typical distance to the nearest region identical to ours. It comes out to roughly 10 to the power of 10 to the 29th meters, a number so vast there's no useful way to compare it to any physical distance you've ever encountered. Far, far beyond the observable universe. Far beyond the event horizon. Beyond any astronomical scale that means anything. But, and this is the whole point, it is finite. The distance is a finite number. Let me make that concrete, and let me make it personal, because the math doesn't care about your discomfort and I want you to feel it. Somewhere out there, at that finite distance, there is a region of flat space the same size as ours, containing exactly the same matter in exactly the same configuration. There is an Earth there. There is a body there with your face, your exact posture, the precise tilt of your head, the specific angle of your shoulders right now. There is a brain there holding exactly the thought you are holding in this instant. There is a heart there beating at the same rate as yours. There is a room there with the same dust settled in the same corners. There is, in that distant region, a moment utterly indistinguishable from this one. It exists. The math says it exists, not once, but infinitely many times, at ever greater distances, scattered across the endless extent of space. And I want to be precise about what this is and isn't. This is not the eternal inflation multiverse. This is not the many worlds idea from quantum mechanics, with reality branching at every choice. This is something far cheaper and far harder to dismiss. This is just the consequence of a flat, infinite universe with uniform physics, the plain reading of the data we already have, before we add a single speculative thing. Tegmark didn't discover the implication, working cosmologists have been quietly aware of it for years. What he did was state it precisely, run the calculation explicitly, and give it a name, so it could be told apart from the more speculative levels, the eternal inflation bubbles, the quantum branching, and the most abstract level of all, the idea that every mathematically consistent universe exists. The level 1 version is the cheapest of them. It requires only standard cosmology. It requires only that the flatness be roughly right and the cosmological principle roughly hold. And it produces this. And yet accepting it is genuinely hard, because the intuition it contradicts is one of the deepest we have. The sense that I am the only version of me is wired into nearly every story humans have ever told about themselves. It sits behind our religions, our philosophies, the entire moral weight we place on a single human choice. The level 1 picture doesn't quite destroy that intuition, because the copies are at distances that are, for any practical purpose, infinite. You will never meet them. You will never send them a message or receive one. They cannot touch your life in any way. The local, lived, moral sense of being a unique person isn't threatened by their existence. But the bare statistical fact of them carries a strange and quiet weight. It's not that there might be another you. It's that there are infinitely many, identical down to the configuration of every neuron, and some of them are hearing these exact words at this exact moment. Some are laughing. Some are setting the audio down and walking out of the room. Some are leaning in closer. Every variation of the next minute of your life that the laws of physics permit is being lived out, right now, somewhere, by another you. There's an even closer version of this that's worth sitting with for a moment, because it sharpens the point. The copies I just described are identical to you down to every last detail of your entire history, and those are the most distant ones. But Tegmark also estimated the distance to the nearest region containing a copy of you that matches only up to 1 second ago. That copy is far, far closer, though still at a distance written as 10 to the power of 10 to the 16th meters, because you're requiring less agreement. It was the same as you a moment ago, and only now has it begun to diverge, making some slightly different choice in the next breath. The deeper into your past you demand the match extend, the farther you have to travel to find it. But for any finite depth of matching, the distance is finite, and the number of such copies, in an infinite universe, is infinite. Sit with the specific physical reality of it. In this moment, you are aware of yourself, the chair beneath you, the air in your lungs, the faint tension in your shoulders, the small sound of this narration in your ears. That awareness is a particular physical state of your brain, neurons in a particular pattern, electrical activity flowing a particular way, chemistry held at particular levels in the gaps between cells. Somewhere very far away, that exact pattern of neurons and electricity and chemistry exists in another brain. That other brain is having the same awareness. It feels the same tension in the same shoulders. It hears the same words. And it believes, just as you do, that it is the only one having this experience. It is wrong. It is one of an infinite number having precisely this experience. And so, the math says, are you? You can resist the conclusion. You can argue with the assumptions, refuse to take the cosmological principle at face value, or doubt the flatness measurement, or decline to apply the counting argument to something as intimate as a mind. Those are all defensible moves. But understand what they are moves against the data. The default reading, the cleanest reading, the reading the working community accepts, says you are not unique. The math kept producing it. And that brings us back, one more time, to the reason all of this is happening at all, the reason behind the reason, the engine that, in the eternal inflation picture, has been generating every one of these bubbles and copies and versions, and is still generating more, right now, while you breathe. That's the heart of why the universe is infinite for a reason. The reason is the engine. The engine is still on. And in the next stretch, I want to walk you all the way into it, and then bring this whole night quietly back down to the chair you're sitting in. It's time to put the engine fully in front of us and look at it directly. We've walked a long way to get here. We've seen that the universe is flat, by the cleanest reading of the data. We've seen that flatness, under uniform physics, means infinite. We've traced the inflation story that explains why the universe is flat, and the moment in 1986 when the same theory revealed that inflation, once started, doesn't stop everywhere. We've stood at the event horizon that hides the still inflating background from us forever, watched it shrink, and visited the one ambiguous fingerprint that might confirm any of it. We've sat through the public fight over whether this is even science, and watched the mainstream defend it as a deduction from confirmed theory. And we've followed the cold, simple arithmetic to the other versions of you that the geometry cannot avoid. Now let's name the thing underneath all of it. The engine is the inflating field, in the regions where it still sits high up its slope, the parts of the universe where inflation has not yet ended. The dynamics of that field, the shape of its energy, the quantum jitters that perturb it, the way the volumes grow and balance under expansion, all of that together is the engine. And it isn't a metaphor. It's a specific physical mechanism, with specific equations, producing a specific behavior. The behavior is this. Regions where the field is high inflate more vigorously, because the local rate of expansion is set by the field's energy. So those regions grow in volume faster than the regions that have rolled down and finished. New finished bubbles keep forming inside the inflating background, but the inflating volume always outpaces them, always makes more of itself than it loses. In the simplest models, the engine doubles the volume of inflating space roughly every 10 to the minus 34 seconds. That's not a precise figure, it depends on the model, but it's the right ballpark for the kinds of inflation that fit the data. Let me make that doubling tangible, because the number is so small it just slides off the mind otherwise. Take 1 cubic meter of inflating space, somewhere out in the background, right now. After 10 to the minus 34 seconds, it's 2 cubic meters. A moment later, 4. After 10 to the minus 33 seconds, it's doubled 10 times over, about 1,000 cubic meters. After 10 to the minus 32 seconds, 100 doublings, and it's something like 1 billion cubic meters. After 10 to the minus 30 seconds, still less time than it takes a single neuron to even begin to fire, still less than the blink of an eye by an unfathomable margin, it has doubled 10,000 times, and that original cubic meter has become a volume so enormous the number of cubic meters can no longer be sensibly written in ordinary scientific notation. By the time a full second has passed, the original meter has bloomed into something beyond any comparison the human mind can hold. That is what is happening, right now, somewhere just past our horizon. It has been happening since before our bubble formed. It is happening at this very moment. And it will keep happening forever. There's a subtle thing to be careful about here, because it's easy to picture wrongly. This growth is not the inflating background getting bigger as seen from some outside vantage. There is no outside. The inflating background is not sitting inside some larger arena that it's expanding into. The growth is intrinsic, the geometry of space itself is changing, so that the distance between any 2 points doubles on that brutal timescale. From the inside, it looks like expansion. From the outside, if outside even means anything, there's no observation anyone could make to compare. The space is growing within itself. The distances are stretching. No external observer could ever watch it from beyond, because there is no beyond. And our own bubble, our observable universe, has the very same character. From inside, we see our local expansion as galaxies drifting apart, and we extrapolate from it. We don't perceive ourselves as a finite bubble floating in a larger inflating sea. But the eternal inflation picture says, yes, that's exactly what you'd see from in here, because you're inside the bubble and you cannot see out. Here's an image that may help. Picture the inflating background as a kind of endless cosmic foam, always frothing up new bubbles inside itself. The bubbles are the finished, post-inflation patches, universes like ours. The foam doesn't disappear when a bubble forms, it keeps frothing all around it. And the bubbles, from inside, can't see the foam. Each one looks, to its own inhabitants, like a complete and self-contained universe. The bubble is their observable patch, and what lies past their horizon, they call beyond. But in the eternal inflation picture, beyond the horizon is the continuing foam. And the foam is not in the past. The foam is happening now, as you listen. This is the part that almost never survives in the popular version of the story, so let me say it as plainly as I can. We're used to talking about inflation as something that happened, a phase the early universe went through and left behind. In the standard telling, inflation ran, then ended about 13.8 billion years ago, and the moment it ended is what we call the Big Bang. After that came matter, radiation, then dark energy and the slow modern expansion. Inflation, in that telling, is history. Eternal inflation says, no. Inflation is not history. Inflation is what the universe is still doing. The phase has not ended globally. It only ended locally, in this one finite bubble we call our observable patch. Everywhere else, in the unbounded background that contains us, it's still going. The Big Bang in our patch was not the end of inflation. It was the local end of inflation. The first fraction of the first second of the universe, the part we think of as ancient, finished, buried in the deep past, has not actually finished in the global sense. It only finished here. Just outside our patch, that very first instant is, in the appropriate sense, still going. The same physics that ruled the earliest moment of our patch is operating right now, somewhere just beyond our event horizon. Those regions are at the same point in their inflationary phase that our region was almost 14 billion years ago. From their vantage, our region is one of the ones that has already crossed over into ordinary, post-inflation existence. From ours, they're the still-burning beginning we can never reach. So this is what it means to be a bubble in a still-inflating cosmos. We are not a finished universe. We are a finished local patch inside an unfinished process. The patch is what we can see. The process is what we cannot, and it continues, and it will continue forever. And here I want to offer you the reframe this whole night has been building toward, because it changes what the word infinite even means. When most people use the word, they use it as a noun. The universe is an infinity. There exists an infinity of stars. Infinity is a thing, a property the universe has, the answer to, how much. But in the eternal inflation picture, infinity is not a noun. It's a verb. Infinity is something the universe is doing. It is the ongoing process of inflation in the regions where it hasn't ended, producing more universe at a rate with no limit and no off switch. The universe is not infinite the way a number line is infinite, sitting there complete and endless. The universe is infinite the way a fire is hot, by continuing to burn. Let me develop that, because it does real work. When a fire burns, the fire is not a state. It's not something the wood has, the way the wood has a color or a weight. The fire is a process, a reaction, a release of energy, a transformation of matter from one form to another. The fire is what the wood is doing. Stop the burning, and there's no leftover fire residing in the ashes. The fire was the burning, and when the burning stops, the fire is simply gone. The universe, in this picture, is like that. It is not a finished object that possesses the property of being infinite. It is a process, an ongoing exponential expansion in the inflating background, making more space faster than bubbles can form. The infinity is not a feature the universe has. The infinity is what the universe is doing. And that difference answers the question the title posed. Why is the universe infinite? Because the activity that makes the universe is still happening. Stop the activity, and you'd still have the patches already made, a large, finite, post-inflation cosmos with no new bubbles being added. The infinity depends on the burning continuing. And in the equations of inflation, there is no mechanism that puts out the fire globally. The phase ends locally in each bubble. The background between the bubbles burns on. The doubling time stays at roughly 10 to the minus 34 seconds, forever. You might fairly ask, couldn't there be some physics we haven't discovered yet that shuts the whole thing off after all? It's a reasonable question, and the honest answer is, probably not. Physicists have worked hard to build models where inflation does end globally, and they can, but those models require very specific, finely tuned shapes for the field's energy. They're possible, but they're not the natural versions, and they're not the ones that match the data most cleanly. The data prefers the simple slow-roll forms, and the simple slow-roll forms produce eternal inflation. To escape the prediction, you have to make the theory more elaborate, and the more elaborate theory doesn't fit any better. That's a large part of why the prediction is taken seriously. It's not just that the math produces it, it's that the math produces it in the simplest, most natural, most data-friendly versions of the theory. To avoid it, you have to work against the grain of the evidence. So the prediction stands. Eternal inflation is the default behavior of the inflation that matches what we actually measure. And there's one last thing to add to the verb picture before we let the technical part go, because it's the part that gives all of this its particular weight. The verb picture says infinity is what the engine produces. It does not say infinity is what the engine intends. The engine has no intention. It's a set of equations governing a field undergoing its dynamics. The dynamics produce eternal inflation as a side effect of how the volumes grow. There is no purpose to the process. No goal. No destination. The process is just what the field does when you let the equations run. So when the title says the universe is infinite for a reason, it does not mean for a purpose. The reason is mechanical, not designed. The reason is simply that the equations, when you solve them, produce a process with no off switch, and the infinity is what the absence of an off switch produces after enough time has passed. And enough time has been passing, in the inflating background, for as long as the inflating background has existed. In its own quiet way, this is more unsettling than if there were a purpose behind it. A universe that's infinite because some agent willed it to be at least has a reason in the sense of an intention behind it. A universe that's infinite because the equations of inflation happen not to include a global stop has a reason only in the sense of a mechanism. The mechanism is real. The mechanism is well understood. The mechanism is the engine, and the engine just keeps going, because that is what its equations say it does. No more, no less. So let's step back now, away from the equations, and come home. Let's come back to the chair, the body, the breath, this moment of attention you've been holding through all of it. We started here, with the simple observation that the empty space around you was once part of a region undergoing this violent early expansion. We moved through what infinite actually means, through the flatness measurement, through the inflation story, through Linde's reluctant result, through the event horizon, the cold spot in Eridanus, the great public argument over whether any of this is science, and the copies of you the math cannot avoid. And we've arrived at the only question that's left. What does it mean to live inside this picture? The first thing to say is the most grounding. It changes nothing about your immediate life. The cosmological structure of the universe does not reach down to what you do tomorrow. It does not touch whom you love, or the work you give yourself to, or the small kindnesses and the small failures of any ordinary afternoon. Those things have their own scale, their own weight, their own stakes, and cosmology does not press on them at all. You are not smaller because the universe is unbounded. The size of the stage was never what gave your life its meaning. The second thing is that it does, quietly, change your sense of where you are. The chair you're sitting in is not just a chair in a finite universe. It's a chair in one finite bubble of an unbounded, ongoing process. The space around your body is a small local result of something much larger that is still unfolding, right now, just past the edge of anything you can ever see. The walls of your room are not the walls of the universe. The universe has no walls. It has, at most, event horizons, and those are boundaries in cause and effect, in what can reach what, not edges you could ever press your hand against. You're inside one such horizon. And the patch you're inside has a particular set of physical laws, the laws that happen to permit stars, and atoms, and chemistry, and biology, and you. In the eternal inflation picture, that's not a coincidence and it's not a privilege. It's just why you can exist here, rather than in one of the other patches where the laws come out wrong, where atoms never form, where no structure resembling a body could ever assemble. You are not in one of those. You're in one of the patches where the conditions happen to come out compatible with a mind that could notice them. The third thing is that you are not alone, and you cannot be. We've followed the counting argument to its end. In a flat, infinite universe with uniform physics, the same configuration as your patch must repeat. Identical copies of you, holding identical thoughts, exist at that finite but unfathomable distance. The math says they exist. The cleanest reading of the data says they exist. You are unique within your own causal sphere, which is a finite, local space. But the universe contains an unbounded number of versions of you, each inside its own sphere, each believing itself to be the only one. And when you sit with that, the usual responses don't quite fit. You can't mourn the loss of your uniqueness, because no version of you is destroyed by the existence of the others. You can't take comfort in the company, because they're at distances that make them as inaccessible as if they didn't exist at all. You can't apply your ordinary moral reasoning, because they stand in no relationship to you. They are simply there. The math says they are there. And the only response that quite matches the fact is to acknowledge it, and go on breathing. And the fourth thing is the one we keep coming back to: the engine is still running. Right now, while you breathe, while you settle a little deeper into the chair, the engine is producing new inflating space. By the time you finish your next breath, it has doubled the volume of that space more times than anyone could count. There is more universe now than there was when you started listening tonight. There will be more by the time you stop. There will be more after you are gone. This is not a flourish. It's the technical content of the theory we use to explain that ancient relic glow, and if you accept the theory, which has been confirmed to high precision again and again, then you accept the engine. The engine is what makes the theory work. The engine is why the universe looks the way it does. And the engine, by the same dynamics, is what guarantees the universe never settles into a final state. There's a way to feel all of this that isn't despair, even though the picture has a certain heaviness to it. The way is to notice that you are part of what the engine made. You are one of the things it produced. Your existence is not in spite of the engine, it's because of it. The same dynamics that drive the endless inflating background also throw off, as a side effect, finite local patches like ours, where things cool and settle, where structure forms, where bodies assemble, where minds come into being and turn their attention toward audio recordings about the cosmos. We are the residue of the process. We are one of the things the engine makes by continuing to run. And here is the strange consolation in it: the engine's continuation out there doesn't sustain us moment to moment. Our patch stopped inflating almost 14 billion years ago, and we've been here ever since in a region that is no longer burning. The fire that still burns beyond our horizon doesn't feed back on us. We're sealed off from it. We are, in a practical sense, free of it. And yet, in a structural sense, we are entirely defined by it. We exist because the engine ran long enough to make a patch like ours, and then went quiet here, in this one small region, long enough for it to cool and for us to come together. We are a product of the process. The process isn't finished. We are an early result of an experiment that has no scheduled end. And that brings us, gently, to the thing the title promised, the reason it called this terrifying. The terror was never the size of the universe. The terror is that the engine which made it is still running. That the process that produced us has no off switch. That the math of our most successful theory of the cosmos does not allow the burning to stop. That we are inside a fire that is still alight, and always will be. Inflation is not a historical event. Inflation is an ongoing process, and we are one of its outputs. But sit with that picture long enough, and the terror begins to soften into something else. Not acceptance, exactly. Not peace. Something closer to recognition. The universe is not a finished thing we happen to inhabit. The universe is a process we happen to be part of. The process is still going. It will go on in the inflating regions beyond our horizon long after we are gone. New bubbles will form. New patches will cool. New structures will assemble. And in some of them, new minds will turn toward their own cosmologies and arrive, by their own paths, at this same picture. That isn't despair. It isn't nihilism. It's just, in the language of a late conversation that runs past midnight, what the data seems to say. The universe is unfinished. We are one of the things the unfinishing has produced. The unfinishing continues. The engine that made us is still running. That was the line we planted in the very first minutes tonight, before any of the structure was built beneath it. We can let it land now with its full weight. Somewhere beyond the event horizon, about 16.5 billion light-years from this chair, the same engine that produced the patch you're sitting in is still producing new patches. We will never see them. We will never reach them. We will never exchange a single signal with them. They are, from where we sit, as inaccessible as if they didn't exist. But they do exist. The math says they exist. And the math, in every test we have ever managed to run, has kept turning out to be right. The universe is not big. The universe is unfinished. And the unfinishing is happening right now, just past where we can see, and it will keep happening after the last star in our patch has burned out, after the last galaxy in our horizon has dimmed to invisibility, after the last observer in our sphere has gone silent. The engine doesn't need us. The engine doesn't know about us. The engine is just a set of equations doing what equations do, in regions of space that will never carry our names. And yet here we are. One small local result of the process. Sitting in the chair, in the room, in the patch, in the bubble, attending to a story about the engine, on a planet that exists because the engine fell quiet here long enough for us to assemble. We are, in this moment, one of the things the engine has made. The math kept producing us too. So tonight, when you stand up from wherever you've been sitting, and at some point you walk outside, and you look up at the dark, try, just for a moment, to hold the whole of it. The light you see is old, and it's leaving. The horizon around us is quietly closing. And somewhere past it, in a place we will never go, the first instant of everything is still happening, still burning, still making more. You won't feel any of it. The night will look exactly as it always has. But you'll know that the space between you and that distant glow is not a finished, settled thing. It's a process, still underway. And you are not its center, and you are not its purpose, and you are not its only result. You are simply here, one of the things it has made, awake for a little while, looking up. That's the whole of it. Settle into the quiet after the thought, if you can. There's no tidy moral waiting at the end, and I won't invent one. There's only the picture, with its strange shape, a finite past, an unbounded future, a small finite present, and an infinite, continuing process humming away just past the edge of sight. There's only this moment, and the chair, and the breath, and the slow recognition that the universe was never a place. It was always a process. And we are one of the things it is still, even now, in the making. Thank you for staying through the long version of it. Rest well, wherever you are. Good night.